Let's have a look at a few important properties of the sample variance. I have a random sample, x1 through xn. That is, my random variables x1 through xn are independent and identically distributed. We denote the expected value of xi by mu, and we denote the common variance of xi by sigma square. The definition of the sample variance is according to this formula, which we before the experiment view as a random variable. We can then show the following important result, namely that the expected value of s square is sigma square. The expected value of the sample variance is equal to the variance of each individual observation in the sample. In this case, it's a little bit messier to prove. That's partly due to the fact that we have a square here and we have random variables both here, and xi is correlated with the sample mean. But by expressing the sample mean in terms of the random variables x1 through xn with some algebra, it can be shown that the expected value of s square is sigma square. There is also a formula for the variance of s square, which I will not cover in this lecture. It is not used very often. And in general, the variance of s square depends on higher order moments of the distribution of the xi's. However, one special case I will cover is the case when xi are IID normal mu sigma square. If I know that the distribution of each sample point is normal, in addition to the IID assumption, then we can say a little bit more. In this case, n-1 times s square divided by sigma square will follow a chi-square distribution with n-1 degrees of freedom. Just as a consistency check of this, that would mean that the expected value of the left-hand side, n-1 s square over sigma square, must be equal to, well, if a random variable follows a chi-square distribution with n-1 degrees of freedom, its expected value is n-1. The expected value of any chi-square distribution is its degrees of freedom, so this would be n-1. In the expectation to the left, n-1 and sigma square, they are just constants, so I can take them outside. Then I have this. After cancelling n-1 and multiplying both sides by sigma square, we see that the expected value of s square is indeed sigma square. But keep in mind, it will hold no matter what the distribution of the xi's are, as long as the assumption is satisfied that they all have an expected value of mu and a variance of sigma square, and that they are IID.